In this session, we have three speakers, Professor Sukhendu Mandal, Dr. Bini George, and Dr. Indranath Chakrabarti. First of all, let me introduce Professor Sukhendu Mandal. Professor Sukhendu Mandal currently holds the prestigious position of Professor at IISER Thiruvananthapuram. His contribution to the field of chemistry are remarkable, and today we have the opportunity to gain insight in his wealth of knowledge and experiences. He completed his PhD from IISc Bangalore and PDF from Pennsylvania State University. He has several hundreds of papers in reputed journals and published many book chapters, and he has been honored with several awards and recognition. He has already produced about 8 PhD students, and 6 more are currently under his guidance. With this brief introduction, let me welcome Professor Sukhendu Mandal.
Yeah.
Welcome you, sir.
Good morning, all. Thank you, Dr. Soumya, for the kind introduction. At the outset, I would like to thank the organizer and especially Professor Pradeep for inviting me to present my talk, whatever I am doing at IISER Thiruvananthapuram. I have a couple of students from this college, and every year we are having summer training. Some of them are attending the talks also. Today I will be talking about the recent aspect of cluster, based mainly on the silver and copper. Before that, let me tell you how I have been nurtured or mentored by Professor Pradeep. I have not done PhD or postdoc, nothing with that. I have done PhD Professor Natarajan from IISc Bangalore, postdoc with Aishman Sen at Pennsylvania State University. But when I came back India and 2014, I met him. So he gave some mantra. First of all, Professor Kulkarni has mentioned there is no negativity in his life. The mantra is that how you challenge face the challenges of getting funding and how to tackle that landscape in Indian academia. So thank you very much for your kind mentorship. And I must congratulate all the Farook College. They have produced the Padma Shri of the country. Let's give a big hands for them. Okay, so today I'll be talking about something related to the cluster. But you know that this year Nobel Prize has gone to these quantum dots. And this is the picture has given for the the committee has given this cape. Those ever liking painting, you can see that the beautiful things. So we can have that as that droplet size is decreasing and according to the color has changed. So that is the fantasy of this research, and most important thing, the discovery and synthesis. This is something related to the chemist. Those are doing the synthesis in their laboratory that they awarded the Nobel Prize. And one of the Nobel laureate Brass has mentioned in 1989 that quantum cluster can be called as a nanocluster. So now think in that scenario, if I try to explain how the cluster, because just our previous speaker, Dr. Sivu, has shown that how things that. But before that, I will try to clarify. There is a nanoparticle, there is the carbon nanodots, and nano quantum dots and cluster. What is the classical definition? If you think about in terms of length scale, 1 to 100 always will be nanoparticle, but there is a 2 breakup, at 20 nanometer and 2 nanometer. If below 20 nanometer, you are talking about 2 to 20 nanometer quantum dot, and below 2 nanometer, we are talking about the cluster. What is this 2 number? So basically at 20 nanometer, that the length scale is metal particle close to the electronic mean free path. That time is showing surface plasmon. Surface plasmon, nothing that is the bulk properties, collective oscillation. So 20 nanometer, you can have observation of the surface plasmon. And what is the 2? The plasmonic behavior will disappear. Metal particle size will be the length of Fermi wavelength. So that's why it is called quantum dots. And that's why 2 to 20 nanometer is the quantum dots. Below that will be quantum cluster. And what is nanodots? Because you are talking about large number of carbon nanodots. This quantum dot or quantum cluster, the basic units will be 1, that is responsible for your structural representation of the properties. But the carbon dots, the basic unit will be more than 1, so that will be replacing controlling the structural properties. So in classical definition, quantum dots have size dependent properties. Size is 220 nanometer. Quantum dots is quantum cluster, that nanocluster is atom dependent properties, which is the range of up to 2 nanometer. And if you think that this is the one of the atom, this another atom, the third atom, the way you arrange, you will get the different geometry and the color will be changed. And Dr. Shivu has shown that our kids are playing around. The way you can arrange, they can get the different type of building. These are the building blocks. They are connected to form the entire structure. Even we can knock one of the atom, put the another atom, keeping the structure same by changing the properties. So why should someone work on that? Because we know that if you go to your university, you can have the course is organometallics. If you come to the MSc, then you will be solid state. So organometallic is the molecular chemistry and the solid state is the nanochemistry. Cluster is basically bridging the gap between the organometallic chemistry and that nanochemistry. When you talk about the organometallic chemistry, you might be knowing the cluster geometry, the icosahedron, correct? And that M13. But if you think about the solid state FCC solids, if you don't bother about the contribution, number of atoms, you will get 14. We know that when clusters are linked some point, because you have just now seen 20 nanometer, if you are showing this is the behavior of the 2 nanometer, this is the behavior of 20 nanometer in the optical properties. But if you think about the structure, if you connect all these things, it will be 14. So 13 become 14. That is the fantasy. You have a 13 atom, when you are forming solid, the entire geometry has changed. We try to figure out how things happen. So the important thing, the atomic properties, you know that this is showing the surface plasmon just now I mentioned. And organometallic complexes, you can see the optical transition HOMO to LUMO. But these properties of this will be the in-between, that is called step-like transition. They are different cluster, they are having step-like transition. Why the step-like transition? Because the states are quantized, there are several transitions happening. And you might have heard study on Professor Pradeep, the nanocluster is a molecule. When you're talking about the molecule, we're talking about the hydrogen peroxide H2O2, we're talking about the water H2O, the exact formula is required. Exact formula is important to know that, and that is the controlling the properties. So if you take the electronic structure of the atomic orbital, they have only atomic states. And we know the bulk particles, they are having the states are basically splitting. There is no conduction band, valence band, they are overlapping. For the nanocluster, we have a states are quantized, they can have jump one electron to other, that's why they can have a step-like electronic transition. And in 2018, it has been shown that you need to have 279 atoms which can show the bulk property, that is the surface plasmon. They have shown that 246 is a molecular-like behavior, 279 is showing that bulk properties. So we are not talking about the size dependent for what Nobel Prize has gone, we are talking about the atom dependent where the properties are dependent. So now question is that what is the difference between the size dependent and atom precision? Let us do a very basic thing. We might be knowing that the gold atom density is the 59 atoms per nanometer cube. You synthesize the 5 nanometer particles. So you try to calculate how many atoms are there. If you calculate, there will be 3860 number of atoms, 3860 gold atoms. When you're talking about the particle size, we are talking about the average, plus minus 10%. Let us take a 5%. Here we calculate 10% will be 500 atoms. So 5.25 or 4.75. There is a difference will be 500 atoms. We'll be able to see that each atom can change the property. So when you're talking about the atom size dependent, there is a difference of few hundred atoms, obviously the properties will be changed. So that is the fantasy work on the cluster. We are talking about the atom precision. When you're talking about the atom precision, you should know what is the crystal structure, because otherwise you cannot have the precision on the structure. You can explain that entire structure, basically there is a metal in a zero oxidation state, that is core, or the classic term we are telling kernel. Then the metal which bond with the ligand, very basic chemistry, when metals are having electron exchange with the ligand, metal has to have some oxidation state, electron transfer is happening. Generally metal is the plus oxidation state, and this is the ligand that we are protecting. Now, three ways to think about it. I do know that what is the property is coming from there, because this is zero oxidation state. Here the metal is a plus oxidation state, that electronic structure will be different, and this is my organic linker. If I do want to need the properties of this, because previous talk have shown beautiful things, dipole-dipole interaction, pi stacking, supramolecular, I can play around with this. That's why he is playing around with the azopyridine siege trans, all these things. I want to look for the properties of this, because we know that yesterday Professor Rangara gave a talk, alloy things. Peter Sebastian had talked the alloy thing. I want to dope copper. So I try to drop on this or nickel, which can change the properties. So if I know the interstructure, I can play around with this. Anybody can play around on this structure. And you might be knowing that even every year, announcing the different years of. 2019 was the year of periodic table. Two gentlemen, Will Castleman, gas phase cluster synthesis, and Will Shivkhanna theoretician, they have shown that this aluminum 13 minus cluster mimicking the electronic configuration of chloride minor. Do remember that this chloride minor electronic calculation above principle, you can do the 1:2 PC. But the cluster is not following that. Cluster is big electronic calculation will be predicting by the Gilliam model. So they have predicted that aluminum 13 minus could be chloride, aluminum 14 will be alkali mark. So entire periodic table can be replaced by the cluster, so that means periodic table can go to 3D. This is the motivation of someone to work on that. So my title is in copper and silver, but today I will little bit talk about the gold. The reason I will explain at the end of the thing. So there is several ways of synthesis, because end of the day we need to synthesize them atomically precise. They can have the purification, because you know the organic chemistry, they run the column, or you can put the crystallization, sometime you get, sometime may not get. And there is another technique called ligand exchange. So if you want to do the ligand exchange, these are the parameters to be fulfilled. Your precursor should have well-defined information in terms of structure. Your incoming ligand should be different than the existing ligand, and you need to activate the cluster. That's some sort of thermal activation is required. We started to thinking the ligand exchange on one of the clusters, the gold 23 is protected by the cyclohexane. This is the structural anatomy. You can see that the gold, this is 7 member, and these are the hub atom, and these atoms are bridging. There is a monomer, trimer, and bridging. And with this information, we started the ligand exchange, because you have a cyclohexane thiol. We wanted to replace with the cyclohexane thiol with the tertiary butyl benzene thiol. So organic synthesis is very known. You can track the mechanism through NMR, where here we did the mechanism through the MALDI-MS. So every 30 seconds, we have stopped the reaction, purify the product, analyze all the product, and we can see that within 60 minutes, we are going to 28. These are the intermediate we have isolated. Then you try to understand how things are happening. We have done the calculation with the Vishwarup Pathak and IIT Indore. They are used our basic chemistry. We know the molecular orbital theory, linear combination of atomic orbitals and two atomic exchange coupling, you need to have it. So we are having that AU4 and AU3 unit that we consider the cluster unit. Then your exchange coupling, cluster orbital theory, we can see that this is the cluster units available in the AU23, and this is forming the AU28, and if you keep on hitting, you will get the 36. Then we replace that. If I do only benzene thiol, what will happen? So we have cyclohexane thiol replaced with benzene thiol. Similar way, we have tracked the mechanism, all the intermediate, and we can see that there is a 4 bridging thiol, because the 16 cyclohexane thiol replaced by the 16 benzene thiol, 12 benzene thiol. The remaining 4, because 25 has 18, so remaining 4 cyclohexane thiol is bonded with the bridging. What is that bridging? Because that thiol is basically connected the kernel, they are not connected with the other side. So the moment it happened, that the distortion is happening, so 23 become converted to 25, that is that. So we have benzene thiol, we have tertiary butyl benzene thiol. Then we thought that the benzene thiol we are getting 25 cluster, and tertiary butyl get 28 cluster. Then we have done the sequence of reaction. This is the benzene thiol. We have sequentially adding methyl, ethyl, isobutyl, and tertiary butyl. And every cases I have mentioned that we have the different products and analyze. And every cases we did the mechanism like previous cases. We can see that we are getting that 36, 28, and the byproduct. Now each cases we can see that when you are benzene thiol, after 48-hour reaction, this is the yield of quantitative yield, not qualitative, quantitative yield of 36 cluster, this is the 28, and this is the precursor. Now the question is that there is a probability 28 at extreme thermal condition can convert to 36. So that this 28 can be converted to 36 or not. We have extended the reaction for 11 days. We can see that the 36 contribution for these three is not changing because these 28 is degraded. So 28 is not contributing. So whatever the formation is happening, 36 from the different pathway. Long story in short, 23, when you are getting two precursor can happen. 23, the new ligands, and 25 with the new ligand. 23 new ligand, what are the, then is that will be go for this, be it benzene thiol, methyl, ethyl, isobutane, trisobutane. When you intermediate in 25, that 36, when intermediate 26, then 28. So what is happening? Simply, because you are having all benzene thiol, only one on methyl are changing, we are trying to understand how the mechanism is happening. One methyl can change the entire reaction pathway. So we have crystallized all these cases, and we can see that the two extreme is happening when you are having the benzene thiol, 36, and yield is decreasing, and 28, that thiol yield is increasing. And this work has carried by your alumni, Nida Kinahan. So now I'll talk about gold. Now we'll go to silver. Silver is challenging compared to the gold because gold is superior to oxide. Silver is redox potential is very low. It can be going to the +1 state. And we are working on to get the crystallized. It's quite difficult for silver to crystallization and solving. First of all, when you do crystallize silver, all reaction you have to do dark. And crystallization, you may get it, but the difficulty in challenging crystal structure solution because it's a large absorption problem and the poor quality data. With that, we have some sort of contribution on this. We have synthesized the cluster of Ag50, which is protected by the tertiary butyl thiol, and this is that. We can see that how I can explain this. This is the Ag50 structure, this is Ag14. We know that A, B, C packing will be the closed cubic close, because Professor Kulkarni has beautifully talked about how the FCC, non-FCC change happening. This is the 14 A, B stacking, this is 24 is kind of bowl, and this is the 12. This is the 50 silver node. This is the S13, this is 2 minus. That is forming the icosahedron. Then if you blend with this, you can have the Keplerian cell structure. The structure is crystallized in the cubic system, but we have not seen any ABC packing pattern. We are seeing the hexagonal packing pattern. That we can see that this is the HCP kernel, this is the other things, and this is the forming, this is the Keplerian cell, this is the overall 50 structure. Why this is Keplerian cell? This cell is look like the Kepler model, who initially explained our galaxy. As I mentioned that the difficulty is in structure. We can see that this one we can crystallographically detect it, but this is not. Reason is very simple. Crystallography depends on how many electrons. X-rays are diffracted by the electron density of the atom. So silver is very heavy compared to the carbon, so that's why carbon is not able to see because we didn't have the good crystal structure. As I mentioned that we are having the cubic structure, but we are not seeing any cubic arrangement in the setup. When we arrange the crystal cluster in an extended solid, we can see that this is the cubic form, the cubic structure. And we can see that the most important structure on the cluster is that fullerene, that is in the FCC form, and this is the foot and mouth virus, our kids generally used to get, that is also having the FCC in solids. And how important the mass spectrometry, because crystallographically you could not able to do the anion, and X-ray ESI mass is detected there. Then have used this cluster for the single crystal for the photocurrent generate, and it's showing the photocurrent generation, it can sustain from few cycles. Next, I will take another cluster we have synthesized, Ag16, is protected by the chlorine, and this is the small cluster and protected the adamantane thiol. Our knowledge on gold basically help us to explore the other thing. Gold cluster calculation is showing that if you have emission properties, that radiative and non-radiative. Radiative part is controlled by the kernel, non-radiative by the surface. So when we thought that we have adamantane thiol, bulky, it can suppress the non-radiative pathway, it can have some sort of emission at room temperature, but unfortunately this cluster is not emissive. So then we have to do that because the adamantane thiol, we protect it with a cap with the beta CD and make a composite, and you can see that though we have 8 adamantine thiol, only 2 can be protected because of the steric bulkiness, and with the composite had characterized by the mass spectrometry. You can see that room temperature Ag16 is non-emissive, 1 adamantine thiol, 1 beta CD, 2 beta CD that emissive, and lifetime has enhanced. Then we have used this cluster and beta CD composite as a donor, appropriate acceptor we have chosen, then we can see the appropriate beta carotene, and there is energy transfer, and it can be used for the 93%, it can be used for the artificial light harvesting. Next, because just now Dr. Sibu has talked about that clusters are supramolecularly arranged the superstructure. What we are going to show that cluster we linked with the linker for the extended structure. That two ways to think about it, because we are wanted to synthesize a single layer of 2D. Yesterday Rahul Nair has given a beautiful talk, either MOS2 or graphene. But here we wanted to do the both inorganic and organic composite. So we have synthesized the Ag12 cluster, which is linked by the azopyridine, and this is the structure analysis. We can see that this is a beautiful honeycomb structure, they stacked in AA fashion. So we have exfoliated, mechanical exfoliation, we got the single layer that we have characterized different type of character AFM and the TM. Interesting feature is that when you have a multi-layer versus single layer, there is a change in optical properties. And then we have done the theoretical calculation where is showing the p-type semiconductor, and we made a device out of the single layer, and we can see that is showing the very good FET device, and this is as per compared to the other cluster where on-off ratio is very high and the mobility and carrier density. So not only we are linking the cluster in the extended solid, make a single layer and use for the field effect transistor. Recently, very recent we have tinkered because that cases we are tinking only Ag12 linked by the azopyridine. We have synthesized a molecular cluster. This molecule is very difficult, small is big. Here small is very difficult because of the stability. With the Ag12 cluster, we have protected with that basically with the pyridine, and another cluster we protected by the big linker with the tripod and nitrogen ether. This is the molecular cluster in the solid state, and this is the two-dimensional structure. We have done the optical property in the solid state. We can see that basically solid state UV absorption and the photoluminescence in the room temperature, we can having that around 600 nanometer, and this peak is coming from the linker. And then this is the solid, molecular cluster, and this is coming from this. So this node this is most of the organic molecular cluster, you are observing this peak. So for the sake of simplicity, you are not bothering this peak, but these peaks are originating from the Ag12 cluster. So now we have done temperature dependent study. We can see that for the two-dimensional structure, there is a shift of 50 nanometer. For the molecular clusters, here is a 20 nanometer. Then we have done the temperature dependent study. Temperature dependent study, we can see that from the difference temperature, there is a transition at participate temperature. For 0D around 167 K and for 2D at 187 K. So we have calculated the field with Herb maxima for the two-dimensional cluster is coming 1115 centimeter, for molecular is 540. Then we have measured the lifetime, and each component you can see the lifetime is increased for the cluster assembled material compared to the molecular cluster. Do remember that molecular cluster is not emissive at room temperature, but 2D cluster is emissive at room temperature. Then we have calculated the singlet triplet gap. For this 0D is 0.06 eV, for 2D is 144 eV. So if we try to think about in this way, then we have done a theoretical calculation for the 0D, that is matching. So basically what you are trying to tune that's the singlet triplet gap. That's the observation we observe in the molecular cluster photoluminescence property. How can I correlate with that? Being a structural chemist, we should know what is the difference of the structure, because we have seen that molecular cluster silver-silver interaction is distant 3.16, for the 2D 3.12. That's the first one. Second one, we can have observed that the corner to corner distance is 2D cam higher, it's 1.3. So that means that the silver-silver interaction is basically controlling the singlet triplet gap of this molecule. Now next 5-6 minutes I will be talking about the copper before I give you the question answer. So copper has more difficult to synthesize compared to the silver. The reason is that because this reduction is even lower, and copper is advantage is that several advantages. Copper is the large abundant, cheap, so you can do any property studies, you can have a real application of copper. Copper have another difficulties because we have seen that copper has a tendency which can breach through hydride. That difficulty basically creates the difficulty in the single crystal quality and creates the difficulty in solving the structure. Copper has an advantage, another thing, it can form the fascinating structure so beautifully. So we thought that we can have the copper because though there are a few reports are there, then some more reports increase, number has increased. So we have synthesized, before I talk to you about the copper synthesis, why this forming different type of structure and what is this? A textbook chemistry, you can see the octahedral, tetrahedral, cuboctahedral structure. These all are classified based on three things. The phase, or the convex polyhedra, phase are matching how. So when convex polyhedron, phases are congruent, identical in shape and size, same number of phases meet each, that is called platonic solid. Tetrahedron, cubic, octahedron, dodecahedron, icosahedron. When phases are convex polyhedra, the convex phases are not congruent. Phases are congruent. Same type of phase. So only different, the platonic solid phases are congruent. When you have Archimedean solid phases are not congruent, that number is 13. This is like one of the examples is cuboctahedron. When both are not, phases are not congruent, they are not meeting each other in vertex, that is called Johnson story. This is of 92 types. So whatever structure you will be getting, we will try to see whether the phases are congruent or they are matching on each other. Based on that, we can classify how we can explain the copper structure. So we have synthesized the copper 18 cluster, which protected by the adamantanthiol and triphenyl phosphine. And the chlorine is one of the bridging ligand. As I mentioned that copper has a tendency to form hydride, and this hydride is quite difficult to locate. So if you don't have good single crystal data, it is quite difficulty. Literature knowledge has shown that copper hydride, hydrogen source is the reducing agent sodium borohydride. I'll talk about how we are detected. So once you have the crystal structure, you can do the NMR or the proton NMR, then you replace the sodium borohydride with the deuterated and do the NMR. You can see that there's a position shift or not there. And from there, you can quantitatively calculate how many hydrides are there. Let me explain the structure. This is the copper, it looks like a beautiful butterfly structure. This is the core, copper 6, copper Cu6 and Cu5. This is the platonic solids, this is the Johnson solids. And you can see that this particular copper is fused to the other two geometry. And this copper is basically, these are interactions, these are not bond. These are coppers basically in zero oxidation state. And we have proved through our XPS and the EPR data. And theoretical calculation showing that the better charge analysis, this copper is different to the other copper, it's close to zero oxidation state. Similar knowledge, as I told, that work on gold has given a proof of principle to work on silver and different type of application. I think Professor Pradeep has long time shown how the supramolecular structure they created by protecting the beta CD. Same concept we have used here because this copper cluster is non-emissive. So, but this case is only, we can have how many? We can, oh sorry. We have 12 adamantane, but we can see that only one adamantane can be protected by the beta CD because of the steric hindrance. So once you have protected the CD, this cluster is emissive at room temperature. This cluster is emissive. So basically, you have synthesis of copper cluster is challenging. We have done it single crystal level and make it emissive by using the host ghost concept. Now I'll try to give you last example where you are talking about basically the isomerism concept. We know that when isomerism, we will have the formula should be same, and crystallographer will tell that PS group should be same, only the arrangement is different. If we relax the definition of this, we have a two component in cluster, metal core and ligand. If metal core number is same, ligand is different, I can tell as quasi-isomerism. So quasi-isomerism, this is the real isomerism, gold 38. We can see that the structural arrangement, they have two different type of optical properties, and this is the quasi-isomerism. We have synthesized a copper 29 cluster. So copper 29 clusters is a tertiary butyl thiol and chlorine and protected by triphenyl phosphine. Then with tertiary butyl thiol, I replace with the cyclohexane thiol. And we can see that we got the identical structure, everything has same, hydride number is same. Only there, this is the tertiary butyl thiol 12, chlorine 6, this is replaced by the cyclohexanethiol. So we try to understand the structure of tertiary butyl thiol. We can see that this is the copper node. We can see that this is that plane, these two triangles in the same phase. Basically, is the Johnson solid. Then another copper cell is that is Archimedean solid, and this is this is 12, 13, 25. This is become 4. So these 4, this is all a virtual band is connected with the 4 triphenyl phosphine. So this is the first cluster where the combination of Johnson, Platonic, and Archimedean solids are there. And but the other clusters where the cyclohexanethiol, that is Platonic and Johnson, Archimedean, Johnson solid is not there. So then we try to understand what is the difference of this in terms, except the number of ligand. We have that this is the cyclohexanethiol, this is that A plane, then we are having that this is the A plane, these two planes are different. The triangle are different. So A, B, C, cubococtahedral geometry, Archimedean solid. And this case you can see that these are in the same phase. That is trigonal orthobiconal like geometry is a Johnson solid. So basically this A, B, A. This is basically FCC and that is non-FCC. So this is the basic difference we have observed in the structure. Then we have done the room temperature emission. We can see that this cluster where the FCC is non-emissive, FCC is non-emissive, and this is the tertiary butyl thiol, which is the emissive. So all other things are same, only the arrangement of the kernel, FCC versus non-FCC, that dictating in their optical properties. So why this happening? Because optical calculation, theoretical calculation showing that the atomic arrangement is connected, different connectivity will be there, that is contributing to the frontier molecular orbital, so that is responsible for the electronic transition. So in summary, we have talked about the one example of AG50 cluster, then we have talked about the AG12, which is used for the light harvesting, then AG12 linked to the azopyridine, we get the 2D sheet, then we have how tune that optical properties on cluster to cluster assemble that basically depends on how the silver-silver interaction. So structural interaction is small interaction reflecting in the properties, and for the copper cases we have the copper 18, beautiful butterfly-like structure, and copper 29 where the quasi-isomerism. And thank you, this is my groups, and thank you very much for your kind attention.
Now the session is open for discussion. Please ask a few questions.
You had FET. What made you fabricate FET? Because is there any advantage in looking at the here mobility? I just missed something. So you are trying to show that you have very good mobility.
Yes.
Okay.
Carrier mobility you have calculated from the experiments.
1.28. Okay. Yeah. No, that makes sense. Good.
Yeah.
Thank you.
You're making so many clusters beautiful. I really liked it. All these clusters are cluster signs that you are actually doing. The synthesis is done at room temperature?
Yes.
So
all synthesis are done
room temperature.
Ambient condition, only for silver we do dark.
Right. Suppose say if you increase the synthesis condition, for example, increase the temperature say let it 5, 10, 15 degrees, will you be able to get the same cluster chemistry?
I can give you the answer that gold cluster transformation where due to the different temperature, but we have number of products, byproducts, everything will be there. So it's temperature dependent because the room temperature, the gold we are replacing cyclohexanethiol for the benzene thiol. When you do 10 degree, 20 degree, 40 degree, because 10 degree you can not only the kinetics, the main product will be more. If you increase the temperature, the byproduct is coming more. And if you go little more temperature, one of the product can be again converted to the others.
So it is basically highly controlled by kinetics and as well as thermodynamics.
Yes.
Both.
Yes. Both controlled by thermodynamics and kinetics.
Any theoretical work done in that?
That is happening in gold. Gold is most established, and that whatever the knowledge you are acquiring from the, but gold is little easy to do also. But silver and copper is a little difficult to do that. But still, gold research has developed. That has done.
Thank you.
Thank you. Student from question. Students?
First of all, I am very happy to see you here in my institute. And my question is, during your lecture, you said that the crystallization of silver nanocluster is very difficult. And what are the methods that can be used to get better crystals of silver nanocluster?
Yeah, there are two ways to answer. First of all, how to get crystal. Second thing is how to get the better crystal. Like how to get crystal, we are playing around the metal salt source. It's not silver chloride or silver oxide. To play around different type of organometallic complex. The reason is that when you metal salt in solution, if you have organic slow release of silver ion, can have that crystallization. And better crystal, that depends on the what metal salts you are using and depends on the what ligands you are using. And better crystal, it depends on that solvent generally. So what solvent, because some solvent crystallization, because solvent of crystallization make it worse the crystal quality. It depends on solvent.
Good morning, one and all. Am I audible? First of all, I would like to thank Sukanya for the nice introduction, and Dr. Pradeep and the EFCS organizing committee members for inviting me for this invited talk. I am from Central University of Kerala, and today I will be discussing the synthesis of some biogenic nanoparticles incorporated bio-nanocomposites and its applications. And this work we have completed with the collaboration work of Institute of Nanomaterials, University of Liburg. From 2014 onwards, we have collaboration with Dr. Mislo Chernig and Dr. VTP Vinod. And this is my current, I have joined in Central University in 2014, and this is my current research group. They are doing some biosensing applications, nanoparticles for biosensing applications and food packaging applications, anti-cancer studies, some wound healing applications, etc. Here, many undergraduate students, I will be discussing some fundamentals of nanotechnology. Nanomaterials, as you know, the materials from 1 to 100 nanometer, and the nanomaterial concept started here by the physicist Richard Feynman. During his famous talk, there is plenty of rooms at the bottom. In 1959, and the term nanotechnology first was used by Norio Taniguchi in 1974. And the applications of this nanotechnology is widely used when Eric Drexler in 1986, he wrote a book, Engines of Creation, the coming era of nanotechnology. And nowadays nanomaterials are used in various application fields, and the transition materials, metal nanoparticles has a wide range of applications. As you all know, there are two different approaches for the synthesis of this nanomaterial. One is top-down approach and other one is a bottom approach. In as top-down approach, the bulk materials are powdered and nanomaterials are synthesized. There is a long execution time and machineries are required for this process. On the other hand, bottom-up approach, assembling of individual atoms and molecules to form the nanoparticles, and there is a short execution time for this. And these are the various techniques used for the synthesis of these nanomaterials by physical methods, top-down, by sputtering, chemical etching, laser ablation, all these methods, and chemical method by using precipitation, electrochemical deposition, sol gel process, etc. And in green method, that is another advanced area of these nanomaterials, by using tissue, these plant materials, bacteria, fungus, etc. And in our group, we are mainly focusing on some green synthesis of nanomaterials. And there is a question why these green synthesis of nanomaterials are important. So these are eco-friendly, non-toxic methods. As you all know this, if you use some chemical methods and these physical methods, then it should be non-toxic, and the physical methods, as you all know, there is some low yield and some machineries are needed, and chemical methods, sometimes we may get these toxic materials and non-eco-friendly and wastage of these chemicals, their disposal, all these are challenging process. That's why we are mainly concentrating on some biological methods some eco-friendly method, and these are non-toxic, and some sterile conditions are used for the synthesis of these materials. And why biogenic process is important? And nowadays here, these are the various fields where this green synthesis and biogenic synthesis are used by using microorganisms, plant tissues, and these are the most applicable area. And the second, and under clinical trial, these are the clinical trial application, magnetically responsive drug delivery, various types of human cancer. The studies are still going on, and nanosensors for the environmental applications. Now I will come to the first part of my talk, that is that we are synthesizing some biogenic nanoparticle materials by using some natural hydrocolloids. And we are using this gum condagogu and gum arabic as the natural hydrocolloids, and these are biopolymers that contains hydroxyl, carboxyl and carbonyl group. And why we are choosing these hydrocolloids? That means most of these hydrocolloids that can act as reducing and oxidizing, and that can stabilize these nanoparticles. First one, these gum exudates are available in Indian terrestrial forest and in some Arabic countries. And the main advantage of this green synthesis of this nanoparticle is it's a single port synthesis. And first we have to take the metal salt solution in required quantity, and the gum, after lyophilization, we have to mix this with the this metal salt solution will be getting nanoparticles in, and after drying and grinding we can use these nanoparticles for the further studies. In the first study we have synthesized titanium oxysulfate hydride solution, titanium nanoparticles by using titanium oxysulfate hydride solution and gum arabic as a precursor molecule that will act as the reducing and stabilizing agent due to the presence of hydroxyl, carbonyl and carboxyl groups. For this we have to simply mix this at 100 degrees Celsius for 1 hour, and after centrifugation followed by calcination at different temperatures we can synthesize the titanium oxide nanoparticles, and we have synthesized at 500 degrees Celsius for 4 hours, and we got the nanoparticles here, and these are characterized by XRD. And we got the nanoparticles with average size of 8.9 and 1.5 nanometer, and further these are calculated by SEM, TEM and IDAX spectra, and we can see the crystallite structure. And from the IR spectra it is clear that titanium oxygen titanium vibrations here that will show the indication of this formation of these nanoparticles. And this is the structure of this gum arabic. This is a biopolymer that consisting of all these hydroxyl, carboxyl, all these groups that can act as reducing and stabilizing agents for the formation of these nanoparticles. And these are the TGA UV visible characterization. And after the synthesis of these nanoparticles, we mainly use the antioxidant studies by DPPH assay that we normally we do with the plant science, and bacterial studies also we will conduct with the help of plant science department. And in biochemistry and molecular biology department we use the cytotoxicity studies. Here we have carried out these studies with the 2 different human cells, kidney cells and liver cells. And here the XTT assay that tetrazoline salts will convert this into formosine dye. And from this cell viability calculations here we will calculate whether these nanoparticles are toxic or, and from the after cytotoxicity screening we will use this nanoparticle for further application studies. And our main application study from my first student was by using we have developed a carbon paste electrode by using these nanoparticles to detect lead. As you all know this in soft toys we use lead metal salts to give intense color, and these children will chew this soft toys here, that lead poisoning will happen or contamination will happen, that will affect the growth of the children and their growth, especially mental growth. And other techniques we use, the IIS and other fluorescence technique, other techniques we use, that all those are expensive. That's why we have developed a method for the detection of lead, and we have collected different samples. We have different collected samples from the locally available market, and we have determined the amount of lead by using the modified carbon-based modified electrode with the nanoparticles. And the electrode fabrication we did by on the carbon-based electrode, we have modified by for microliter titanium dioxide with naphthalene paste, and that is in DMF, and it is kept for drying. Sorry. And this worked as a working electrode in electrochemical workstation. We carried out the studies, and the results are compared with the atomic absorption AS. Okay. Now I will conclude the first part of our studies. Titanium dioxide nanoparticles were synthesized by using a green method, and the structural physicochemical characterization were carried out. And after the antibacterial, antioxidant and cytotoxic studies, the best systems, non-toxic systems were used for the development of this electrochemical sensor electrode, and we have detected this a real application of this detection of lead from these plastic toys. Now moving on to the second part of this here we synthesize some green synthetic method by using plant extracts, Muscenda frondosa, that plant leaves here that consisting of a lot of phytochemicals that will act as reducing and stabilizing agents. These plant leaves were cleaned, shade dried and mechanically grinded, and this plant material is used as a precursor materials, and we have synthesized the nanomaterials. The colloidal solution was lyophilized and used for the further studies, and this is mixed with this metal ion salt solution, and the color of the solution changed from light yellow to reddish brown, that indicates the formation of nanoparticles, and the resulting solution was held at 80 degree for 1 hour for the stabilization time. And here you can see the color change of this nanoparticle solution, and this is further characterized by the FTIR XRD, and the particle size from 10 to nanometer size we got, and these are characterized by some TEM, all this, and these were found to be crystalline in nature. And this is from this we have synthesized this chitosan, is a biopolymer, chitosan silver nanoparticle bio-nanocomposites. And these bio-nanocomposites in different compositions we have synthesized, and we have used that for food packaging applications. And there are different characterization methods, swelling characteristics, water retention time, all these are reducing rigidity, mechanical and physical characteristics, all this we have characterized. And the cytotoxic analysis of these films are carried out because we are using this for food packaging application. The cytotoxic analysis were carried out, and the cell viability of the cytotoxicity of the films, and this found to be non-toxic, and we got about 85% of cytotoxic cell viability and 15% cytotoxicity. And these films were used for food packaging applications, and this was kept till 10 days. Here you can see we have used the normal polyethylene film. Here you can see cut pieces of carrots were wrapped in these films, and then here you can see the color change of this. And the second one is here, this chitosan modified bio-nanocomposite films. Here you can see that carrot pieces were almost remaining same. And here we have successfully produced some packaging films for naturally derived biodegradable polymer materials from chitosan and gelatin. And the synthesized nanocomposite films were characterized and they were used for the food packaging applications. The chitosan gelatin films were least opaque and the opacity of the films increased upon addition of silver nanoparticles. The physicochemical and mechanical properties of the fabricated films are slightly altered with addition of silver nanoparticles. And the main interesting factor of this, all the films are biodegradable. We did the soil testing and indicating spontaneous biodegradation under soil environment. And this chitosan gelatin silver nanoparticle films emerged as a promising antimicrobial packaging material that can expand the shelf life of carrot pieces or any food material. Now moving on to the third part of our study, we have synthesized some cerium dioxide nanoparticles for the effective sensing of this dopamine. Dopamine, as you all know, it is a happy hormone. In the absence of this hormone, this dopamine or from low levels of this dopamine can lead to the diseases like Parkinson's, Alzheimer's, dementia, etc. Here the particles were synthesized in nanometer range and some sort of agglomeration was there, and the SEM EDAX confirmed the presence of cerium and oxygen, and these are spherical morphology and highly crystalline, and average particle size was 14 nanometer. And this was cerium dioxide nanoparticles were modified in a bare glassy carbon electrode, and that was further used for the detection of this dopamine, octamine and tyramine. This octamine and tyramine we have used to study the interference studies. And all these octapamine and tyramine, these are catecholamines and decarbonization products of amino acids of tyrosine. And these neurotransmitters helps to regulate the blood pressure and considered false neurotransmitter. It displays large amounts of noradrenaline that enters the bloodstream and causes vasoconstriction. Here we have synthesized the nanocomposite by using this cerium dioxide nanoparticle with chitosan and gelatin. And chitosan is a natural polymer and it is non-toxic, biodegradable and biocompatible, and it is abundant and renewable, and by simple acetylation reaction we can convert, and these are mainly used for drug delivery systems, water purification and tissue engineering, and this is the structure of this chitosan. And after acetylation, and this cerium metal salt solution, we will be getting cerium nanoparticles and we will get a nanocomposite. And these are the characterization by using FTIR spectroscopy, XRD and SEM analysis we can characterize. And the CV profiles were studied by using this with modified glassy carbon electrode in presence of octamine and tyramine. And we have effectively determined the presence of this dopamine in ppb levels. And bionanocomposite was prepared from chitosan and cerium dioxide nanoparticle solution by using solution casting method, and it is characterized by XRD, FTIR and FSM. The cerium dioxide nanoparticles modified glassy carbon electrodes were employed for the electrochemical detection of octamine, tyramine and dopamine simultaneously, and there was no interference, and the fabrication of the sensor is used for the simultaneous electrochemical detection of tyramine and dopamine, and the modified glassy carbon electrode showed very good sensitivity, selectivity and low detection limit towards the neurotransmitters octamine, dopamine and tyramine. I think I have finished before time. And we have similar method nowadays. Now we are using some wound healing applications and anti-cancer activities. And recently in Astra Medicity, we read that mercury in this fairness creams, a lot of this we have developed electrode for detecting that mercury that is affecting kidney cells. Now, students, if you have any clarification.
Now the session is open for discussion. Please feel free to ask some questions.
Well, this is not a question, just for a clarification. I wanted to know, go to your slide number 15. Yes,
Yeah.
here. So, it is written as microampere, so 0.00 something. So, are you really measuring several sub-nano ampere?
We did it in ppb levels.
I know, but are you really getting this kind of currents?
Yeah. Electron.
Which instrument did you use?
CHN analyzer, CH analyzer, 110 electrochemical workstation.
These measurements are in the ppm level, and I'm wondering whether these
I'll
currents
just
are...
check. I'll check one more time and tell you, sir.
Yeah, thank you.
Students, any clarification?
Ma'am,
Yeah.
what is the limit of detection of lead in first part?
506 ppb and the limit of quantification was 1.68 ppm.
Thank you.
Thank you all the organizers and Professor Pradeep for inviting me to come here. It was a great moment yesterday we had with interacting a lot of students, and I personally enjoyed that particular part. Today we will talk about ligands engineering in atomically precise nanoclusters. That was the title basically, and I will show you how we can engineer ligand, and that will entitle in different kinds of properties to that kind of piece of matter. Before going to that part, so just to brief you about where I am from IIT Kharagpur, which is the eastern part of India. This is the beautiful campus, and this is the first campus of IIT. And here we had a specific line mentioned that it's dedicated to nation. That is what it is trying to do from all the things. And this is the famous gate which we have currently. So this is the new gate of IIT Kharagpur. And this is the building where our department is there. That's the School of Nanoscience, where we have currently almost 17,000 students across 16 disciplines in our entire IIT Kharagpur, and almost 800 faculty members. And we are also encouraging young students to come up for an internship. So if you are feeling that, you may write me. And I am also associated with Indian Academy of Science, where we take summer students. So this time we'll also have some of the summer students. So you can take that opportunity as well, which will be funded well enough. Okay, with that, so we move on to nanoclusters, and you have already heard of too many nanoclusters, and you already know the basic of nanoclusters, that's I assume. But even if you missed it, just to give you a brief summary of what is nanoclusters, they are of small particles. So there is no significant classifications between, you cannot say them a nanoparticle or something. I would say this is a class of nanoparticles, because still they are nano size in terms of size, right? So they are a class of nanoparticles which falls in the size regime of roughly 0 to 3 nanometer, I would say, because there is no specific boundary. Some of the recent discoveries comes up which suggests that there are boundaries, but still it's not clear, because that depends on several other factors, and one of the factors is ligand, which need to be accounted there in order to identify where is that barrier, where plasmon and other started overlapping. So these are as a molecules, as Professor Pradeep says, Professor Sukhendu Mandal says, and Shibu said, that these are molecules. It has molecule-like properties, it has molecule-like structures, it has molecule-like, just like same as a molecular formula. So everything, and it works out beautifully. The good point about these clusters, and the simplest point of these clusters, is you can just measure an absorption spectra, and you can identify whether this is you created some clusters or you created some nanoparticles. So that's the classification, I would say. Measure a spectra, either they will be like featureless or they will have different kinds of band structure. They do not have a plasmonic nature. Then you can consider them that they are clusters because they behave like a molecules. Okay, so moving on, as we know that this figure was like created in 2012 onwards when I was working on this chemical review, but it's still valid, and this goes like exponential. You see it pops up there. Actually, it's popping up enormously, as you have seen just like one lecture before, Professor Sukhendu Mandal has presented. Now, enormous growth is happening on this particular aspect, starting from silver, gold, palladium, platinum, all aspects of different kinds of metals are now coming up to this particular field. And there are plenty of clusters nowadays coming up, like starting from AU25, AU1 or 2 to silver, and you have seen copper 29 as well from Sukhendu Mandal's work. So what are these molecules, and what today we'll be talking about is basically the other aspects of clusters, which is the metal core you most often have seen. Even Professor Sukhendu Mandal have presented. There are three aspects: metal core, then the shell, which contains the metal 1 state, and then you have the ligand part. And today we'll talk about how ligands can control different aspects of metal clusters. And we had elaborately written a chemical review article, another chemical review article on this aspect, especially on nanoparticles, how ligands interact with nanoparticles and what kind of ligands are there, or what is their roles. So if you're interested about this, a broader review article where you have all these aspects of ligands taking important role in nanoparticles interfaces. So we'll talk about nanoclusters, ligands role in nanoclusters, especially on synthesis, properties, and I'll show you some of the applications, how it helps in engineering ligands. So what happens when you have ligands there? We start this entire process by creating clusters. How do we create? So far, that was very mysterious aspect, and as a chemist and entire thing, I hope a lot of chemists are there. We are a very nice cook, right? So all of us cannot say that we are not a cook. Everybody can cook. And the cook depends on how you are putting all these recipes together, and that gives us the taste. That's what all people say. Indians are best in terms of that taste. Because you know, even not in Indians, there are across other global parts where you can have generate a taste, because that taste defines how much quantity you are adding, what quantity you are adding to that particular context. So that is how it started beginning. And you see what we created in our lab. That was Uday Bhaskar, one of my senior, who created this solid state method. Solid state method is nothing but pasting all these materials in under solid state condition, and then you grind it up, and then you extract the clusters. And if we put those different types of ligands, you might get different types of clusters as well. That is what we started working on that aspect. And you see this starts with silver, which is the precursor. Then you mix with the ligand. If it is a solid ligand, you would say it's a solid state method. If it is a liquid method, a liquid ligand, you can say a paste-based method, because ultimately it creates a paste. And then you add the reducing agent, which is basically you have to add, because you have seen that structure of clusters goes from code 0 to 1, and then the ligand parts, right? So you have to reduce it, and that is where the sodium borohydride takes part. So sodium borohydride adds up, and then you see the color changes because it started reducing. It started reducing, and eventually you see this black color. That is where we say that, yeah, clusters are formed. But now what happens next? You have to extract them. You have to extract them in solution, because you need to characterize, different characterization techniques are there, you need to characterize. And then it goes to the next step, which is the purification process. And thereafter, it started working on different aspects of clusters. You can purify, and you can characterize them. Several clusters what we have designed so far, like it starts from gold to silver, Ag44, and then it starts with Ag29. Some of the cases we have created Ag25. There are many other clusters that can be created. Eventually, what I was interesting, like one of the Sukhendu Mandal's slide, where people try to discover about the gold aspect, right? Where from this plasmon starts evolving. That was one of the interesting questions when I was working also during 2020 to 2012. That time we had a question that, yeah, plasmon means surface plasmon resonance, right? That's typically we have seen for the silver cases. Now, for the thiolated cluster cases, where from this started evolve? So we are very curious, and we started creating different types of clusters and tried to measure where is that boundary. Is there really any boundary? What we find out that there may be a boundary where we can go little bit. That's AG114 to AG152, because 152 onwards, we started creating that plasmons. That plasmon started appearing. So we thought that the barrier, what we thought, that plasmon and the molecule-like barrier, that might start from this 114 to 152, but still it's a long window. And what we also realized eventually that this also depends on ligands to ligands, what is there on the surface. If you have a sulfur, if you have a chlorine, if you have other ligands, that vary a lot. So depending on what kinds of monolayers are there on top of this surface, that basically dictates what kind of property you are evolving. So I feel that there is no still clear boundary, but we are working on that, and this is an open area. It's a large open area where people can work in and bring inputs there. So this is one of the aspects which I wanted to show you. Now, what else we can do from ligand engineering? We can do ligand engineering to create nanoscale surfaces, variety of nanoscale surfaces. One of the example is here, like I synthesized Ag44 and then I incorporated on a surface. It's a plasmonic surface, and then we irradiate with the laser. What you see here, that in presence of laser, the mercaptobenzoic acid, 4-mercaptobenzoic acid, that carboxyl part goes up. So basically CO2 release from there, and then you get a phenyl thiol. Basically that's the part. And since this is happening only in the local region, so you can create a pattern out of this. So basically an invisible pattern which you can just see using a Raman microscope. So that is what we try to create. There are many other things which you can try to create there as well. Like for example, we know just before like my presentation, Professor Sukhendu Mandal has shown that this year Nobel Prize got on quantum dots, right? And quantum dots are fascinating. They have exciting colors. You can see a wide variety of colors which covers from 300 to 11,000 nanometers. They have a bright photoluminescence quantum yield as well, and that is why it comes up. When it started and from there it comes up almost 99% of quantum yield. But where we are lagging as a nanocluster chemist, or I would say, is that aspect, that photoluminescence quantum yield. If you think of entire application domain where we need like LED or even bioimaging, any aspects, they have a lot of advantage because they are atomically precise in nature. Some of them are less toxic even than quantum dots. But the major lagging point is compared to the dye or compared to semiconductor quantum dot is their photoluminescence quantum yield. And that is where we need to work on, and I started thinking of how do we enhance that. So how do we enhance the photoluminescence quantum yield in such a cases? So in order to understand that, I need to go back to the fundamentals, and the basic fundamentals of photoluminescence quantum yield is all about Jablonski diagram. I know everybody or most of you know about this fact, this Jablonski diagram that explains the molecular fluorescence, right? So what are the processes that can help us? Because once you excite the electron from ground state to the excited state, I need to stop there, or I need to stop somehow the non-radiative decay process. That is what is the major way, or you can enhance more population of that. These are two major ways that you can enhance the photoluminescence quantum yield. So what are the processes that you can stop non-radiative decay? There are many ways that you can rigidify the surface. You can make it more and more, like basically you have to molecular rotations and vibrations that you have to stop somehow. Like you can freeze it, that's the way that you can do it. So these are typical processes that you can do it. But can you do it based on different types of ligands? Yeah, there are people who have reported different kinds of ligands that can be added on, like bulky ligands that can add on a steric environment to this surface, and you can create those aspects. So when I was working on this problem, then I thought of, okay, let's try of creating or engineering ligand surfaces and see whether that can give us some results on these aspects. Because so far what we observe, organic soluble clusters, whatever this specific case, Ag29, BDT, which you have seen also, they have very lowest quantum yield, almost 0.9. But in the same context, the Ag29 with the DHLA, which is an aqueous soluble ligand, they have a very prominent photoluminescence quantum yield. And if we go back to the series of clusters reported so far, most of the water-soluble clusters, they have a high photoluminescence quantum yield. So what was the reason that could lead us to the mechanism? That is why we drag into this particular problem. And what we find out that if we exchange this Ag29 BDT DHLA, it enhances tremendously. The photoluminescence quantum yield almost 44 times double, 44 times enhances. So now the next point is what is the thing which is happening here? So we try to like understand the process eventually. measured the mass spectrometry. That is the first thing what we need to do and ensure that ligand exchange has happened. So we carried out kinetics, dynamics, everything as much as possible, starting from fluorescence database kinetics, fluorescence absorbance database kinetics, because that's a process. It's a dynamic process. We need to identify where it ends, whether it's giving us 44 or it can give us something more and more and more. So that is where we got that there is some point that the ligand exchange has stopped. Now we need to work out how many ligand exchanges are there. That we need to find out. So we went for a mass spectrometry-based analysis where Ananya, who is one of co-workers there during my PhD time, she was there in Germany. So she helped us in measuring the mass spec, and Professor Kappa's group from Germany, they helped us in mass spec measurements, where we find out that the DHLA, which is basically the dithiol, so they exchange the maximum 6 number of ligand exchange was possible. That is what we find out. So it's a confirmation that you have a ligand exchange. It is nothing unusual things that happen. So it's a ligand exchange things that happen, and only 6 ligand exchange was possible. That is what we came to know. Now we need to figure out why 6 ligand. But even major problem was we don't know even the structure of Ag29 DHLA, because that's a water-soluble clusters. And if you go across all the crystal structures of silver-based or gold-based, most of them, apart from the AuMBA, all of them are organic soluble one. So water soluble, it is very difficult to get a crystal structures. So we need to know the structures. In order to know the structures, what we did an ion mobility measurement. That is what you have seen the last data, which is basically kind of a DLS that separates ions based on their size. And we also have a possibility to measure that size in the gas phase. So you can trap that ion and you can get their ionic size, right? And you can also calculate, because if you can design a model, you can calculate. So you have a possibility to know which isomers are present on that particular cases. Because you can get the data from IMS, the CCS value, and you can calculate it from your theoretical data. And with this, we try to come up with a solution, because the carboxyl group, if you exchange the lipoic acid, they might have a possibility to place it many other places, many other orientations are possible. And from there, what we find out, this is probably the best possible way where you have the 0-0 relative energy. But again, it's also one of the important points which I should mention here, that these are dynamic process, right? We cannot assure a solution-based chemistry directly to a gas-based chemistry, because gas-based chemistry might differ, but we do agree, and there are a lot of other reports which suggest that solution phase chemistry can be reflected in gas phase. So sometimes we have to rely on that aspects, and keeping that in mind, this is probably the best possible direction of carboxyl group anchoring opposite to the metal surface. Now with that, how we can go to the clustered structures, and we have calculated a lot of these, because that helps us a lot to understand. Previously, only optical property was the only calculative from the calculative point of view, that you can compare their calculation spectra, optical spectra, and you have the theoretical optical spectra, and experimental you can verify. But now we have also show another point, that you can get it from what type of structures you have, the isomers you have, that you can get it from the IMS data itself by calculating just CCS values. So now the question again comes back, that why exactly that went up 44-fold enhancement? What are the specific reasons here? Now we have done several kinds of experiments to know the fundamentals behind that. We went for triplet state understanding. We went for aggregation-induced emission. That was one of the major points which comes up in recent days. So we aggregated based on pH values, and we see nothing happens there. So it's not an aggregation-induced emission. Now what exactly is happening is what we saw in mass spec, that there is a dimer. Professor Pradeep has mentioned that dimerization occurs between clusters, right? So that dimer is, if you look at the dimer now, this dimer is basically suggesting that you have, you can freeze the molecules, right? So once you freeze the molecules, that's a clear classification that you can decrease the non-radiative decay path, because you are freezing the molecular rotations, molecular vibrations there. So that is probably what we feel that's one way of explaining the fact that that is the reason somehow that is reflecting. But is it that only reason? But probably another possibility is that this carboxyl group anchoring on the metal surface. So there is also possibility from intra-cluster charge transfer from one carboxyl group to the other clusters. So that might also add up to this process. But nevertheless, we find out that more and more carboxyl group to the system, can help a lot. We did a control experiment with polymers and proteins where we have lots of other things which just absorb on the surface, and these are not aggregated again. We have validated that. So if you add that kind of protein, that enhances further. This is not only on AG29, we carried out on other experiments like other clusters, alloy clusters, and that gives us the same kind of understanding that if you have carboxyl group on that surface, that enhances the photoluminescence quantum yield. So basically, what we came to know from that aspect, that ligand, if you can tune it, then you can have a chance to either decrease or increase any types of possibilities. But that was an enhancement-based experiment, and we also did another experiment here where we try to change the carbon chain length, starting from C1 to C2 to C3 and on. Because the R and SH part, we kept it same in the first experiment. I just wanted to see if we keep the carboxyl group separate from the metal surface, how does it impact? And we also did an experiment that if we modify the carboxyl surface, because carboxyl group mostly negative charge, so if you modify it with an amine group, right, how does it help? And we also tried to carry it out if we oxidize the cluster surface, how does it help? In all these cases, what we know that they have a strong impact on photoluminescence property. Although what we can clearly say from these results that ligands playing an important role in promoting the photoluminescence quantum yield. But is it the original reason for their appearance of fluorescence? So that was one of the controversial questions which many people try to understand. But what we try to point out here that even without any organic ligand, cluster can also be luminescent. But there are inorganic ligands. For example, this was a cluster which was synthesized by laser ablation method starting. It's a top-down approach rather than the bottom-up approach. So where you create clusters using gold foil, first you create a bigger size nanoparticles, then you do another laser ablation process to break down to a small size, and you have only inorganic ions there, chloride minus, Cl minus, OH minus in your solution. You can change the ions. There also, what we saw that clusters are luminescent. So that gives a clear indication that not just the ligand which is important or origin of that clusters. Well, and people are debating now like whether kernel is taking major role of that luminescence part or the ligand to metal charge transfer, that is the leading part. So this experiment, some of these experiments also suggest that yes, indeed, the origin of luminescence might be towards that kernel, which is basically the metals part, metal core part, whereas ligands play an amplification role, like they can promote, they can decrease, they can modify. That possibility is there from the ligand aspect. So with this, we now categorize different kinds of ligands for a specific clusters, like we can make them just like a coordination chemistry. We know we have a primary set of ligands, we have secondary set of ligands, so we can now categorize them. So as I said, which I just add to the Professor Pradeep's point, in that table, if you remember, what are the molecule-like properties which you have on the right side, if you remember that slide. So there you can add on this part as well, that it can slightly closer to that, like it's fitting in there itself, that it's close to a molecule, so where you have those kinds of primary ligands surrounded by secondary ligands. And we have written a nice review article on this, so if you are interested, you can have a look on this. The other aspect of ligand engineering is basically the surface engineering. So one side you can engineer the ligand, the other side you can anchor that ligand to another substrate. That is what basically the hybridization comes in. So you can link in, because that's basically the surface which is interacting to the other molecules or other particles, right? So there also you can do it in several ways. We have seen Sibo as trying to explain that ligands can be ordered in different ways, right? Those all interactions are same, like important here when you try to create two metals coming together through the ligand part. So it can be through metal-ligand covalent interactions. If you have a carboxyl group and a metal, you can try to interact with them. Or it can be through hydrogen bonding, or it can be electrostatic, or it can be just a physisorbed on the surface, right? All these possibilities are there, and we also wrote a nice review on this particular aspect. So if you are interested, you can just have a look. This was one of the experiments which we did during my PhD time, that we tried to anchor silver clusters, silver 44 clusters on tellurium nanowires. And tellurium nanowires, if you anchored them, initially we thought, okay, we anchored them, but what is the big thing, what we get it from there? But the major outbreak came when we tried to assemble them, because one of my senior, Anirvan, so he was working extensively on tellurium nanowires. And I saw he was doing Langmuir-Borges self-assembly process for different aspects. Then I asked, like, when we incorporate clusters on tellurium nanowires, let us see, is there any change happens on that particular aspect. So we saw in normal, like naked eye could not see it, but when we put it in a microscope, we saw that tellurium nanowires, which are originally arranged monolayers, they are now crossed bilayers. And these crossed bilayers, we did several experiments, and then from there, what we find out that this is because of intra-cluster hydrogen bonding. So clusters are sitting on top of tellurium nanowires, and the ligands, basically the mercaptobenzoic acid, the carboxyl part is anchoring on the outside, right? So when you have the other side, you have also a tellurium nanowire where clusters are sitting, mercaptobenzoic acids are there, and only at a specific angle of 76 degree that happens. So we computationally probed why it is because there are more number of hydrogen bonding that is that is the most feasible way to get that kind of hydrogen bonding at 76 degree angle, and that is why it is strongly stabilized, and we form a big layers of bilayers. Now, if you increase the concentration of clusters on top of tellurium nanowires, it forms bundles and several other things we have carried out in that paper. If you're interested, you may look at that. And based on that, since they are strongly interconnected now in a bilayer, you can use them as a strain sensor. This is nothing to do with cluster again. This is to do with tellurium because they are strongly connected. So if you can just bend it, then you can get a response. And based on that, you can play around and make a strain sensor out of these things. With this idea, what comes next is that if clusters can form hydrogen bond on top of a tellurium nano surface, why not they can form directly there, like a freestanding membrane, what we have seen. So freestanding membrane, that is what the next goal. And we did carry out these experiments and find out that a monolayer of clusters, self-standing membrane is possible with the same methods which we try to create there. And you see nice hexagonal patterns are there. And then immediately we came to know Professor Nanappa is working on the other aspects of on macro scale. And then we collaborate together, and then we came up with a nice paper after a long time. So that's also basically leading to a cluster interactions via ligands hydrogen bonding. We can anchor this on other substrate as well. I have carried out on many other aspects. So one of them is here, which is ZNO tetrapod. So zinc oxide is basically, they have a very nice structure. You can anchor clusters. They have a porous size as well. And the clusters, you have a free carboxyl group, which can anchor on the zinc. That's basically a very strong binder for the ligand that you can add up. And that leads to a nice structures. And we did a lot of photoluminescence-based experiments on this particular aspect to know what are the changes addressed on that particular aspects. So moving on, one important point what I wanted to mention for all the students or as a scientist or as an academician, what we see as a research, like some of them ask, like, how do you see as a research? Research is basically like we have two eyes, right? So whenever we do an experiment or we're doing something, we also think about two aspects. That is how the nations or any other science visionaries comes, right? So one eye, we look at the translation of the research as a product, right? What would be the other eye? The other eye is to educate you, to translate that research to an education. And that is what one of the students last time asked, like, how do we change the syllabus or something comes up to this in. I would suggest that more and more such things is needed right now. We should not be just restricted on those long backdated British Empire syllabus now, and moving on, we need to incorporate more and more. In order to do that, so I started thinking of that aspects and designed a laboratory course which student enjoys a lot, starting from University of Hamburg to even IIT Kharagpur. So what was that? This was a famous, this took a lot of time actually. There's a famous story behind that. This was the first paper which I had with 100 comments because it went to college teacher and they are very much on fundamentals, and they asked 100 questions and it went to 3 revisions, and later on I received this comment from the reviewer which clearly says they are very much enriched with this and fascinated about that. They wanted to start this as their one of the curriculum practicals. And in University of Hamburg, I started working on that, and I see the students are enjoying doing that practicals. So more and more such things, what I feel is needed, because this also gives you a feel of how exactly these are, not just listening to the lectures. Rather, if you do it by your own hand, then you will feel, because these are lots of fundamentals, starting from bottom-up and top-down process, right? So this cluster gives you that kind of two domain together. Like you will get to know about bottom up, you will get to know about top-down approach, which is the basic fundamental for all nanomaterial synthesis or material synthesis. So in a same, and you just need an UVVs and FT, and even if you don't have fluorescence, that does not matter. Just UVVs itself, that is enough for you, and it costs just 10 INR per student. So it does not cost a lot. Sometimes people say you are working on silver, that might be costly, but no. If you do it in a bulk scale like 100 students, just 10 INR per students. And UVBs is nowadays, ACRB has a strong funding of SURE, so that promotes at least minimum facilities. So I would expect UVBs should be there in PG labs, and that would be enough for that kind of experiments. I would encourage all the college teachers or other members, they can incorporate these things in their syllabus if possible. As an IIT background, so we have the liberty to do it in our department and our institute, but I know in university it is very difficult. So that can be encouraged eventually. And now coming back to the final conclusion, this was again, I started with my chemical review thing, and now ending up with that. This was we designed in 2012 onwards, and the same thing valids because there is an ocean of opportunities, even with ligands, even with clusters. So you still, that is valid starting from synthesis and isolation, characterizations, the applications. There are enormous possibilities on this particular field, and I feel that there will be more and more youngsters who will be taking up further, and that can be added up in our next generations. So apart from ligand engineering, we started learning. This is not just I say I started working. I started learning on these other aspects, which are basically this, which my groups, we just started stabilizing in IIT Kharagpur. And we are planning to learn more about these particular other aspects in our lab. And this is my small group at IIT Kharagpur. And I thank all of you for your patience and all my funding agencies. In case you are interested to log in, you can just log into my website and see if you have a possibility or you feel like you can plan for an internship, then absolutely fine. Thank you very much for your understanding. Thank you.
Panchilovsky, the naked particle in water and inorganic solvent.
Yes.
And what did you observe?
Yeah, we did. That was basically the basic collaborations we wanted. We had a project, common project, DFG project, running on that particular aspect, that where from the photoluminescence starts in nanoclusters. So we worked on, like they gave us the LFL method, nanoclusters, and then we started working on adding up different ligands with different functionalities. So then we added up, like we changed the head group, we changed the tail group to see whether thiols, basically what we find out that they oxidize the surface as soon as you add them on the surface. Whereas others, nitrogen and phosphorus-based ligands, they did not oxidize the surface. And that leads to a very nice luminescence coming up. So you have that, but you are enhancing that part. But the origin starts from there itself.
Yeah, but the naked one, when
Yes.
he produces it in organic solvent,
No, in organic solvent they cannot produce because that's a laser ablation and they need ionic ingredients there. So they cannot do it in organic solvent. That was their difficulty. They need to do it in ionic, some ions need to be there.
And if you take water, right, and you take the naked one or any of a fluorescent water soluble, and you start adding ethanol, for example, do you get the fluorescence to go down?
It will precipitate immediately. It will
Immediately.
precipitate immediately. And one of the major thing is what they feel like that large scale preparation for them is easy, but the concentration will be very, very low.
Very low.
Very low, very low.
Yes, I know.
So you need to add more and more ethanol to this system to make them precipitate. But yes, you are true, like in that sense, if you add that ethanol part, they will precipitate because they will not stable for a long time, yes. But once you incorporate the ligands, then they will stabilize, yeah.
Can I ask another question? So I want to understand better the idea that you have of the dimers as being the font of the fluorescence. Because if that's true, then your enhancement is much larger because only a fraction of your population will be in dimeric form in solution. And so your real enhancement is not 64, it could be 640, 6,000, depends on the percentage of molecules that are in dimers.
Yes. I absolutely agree that point. So we said that we completely, complete understanding of that mechanism is still not clear to even us. We are trying to understand more and more, but what we find out that this could be the factors. One of them is the dimerization, the other point is the carboxyl group, they can anchor on the other cluster surface, and they can freeze the molecular motions. That is what is also one possibility, right? So that's what we feel so, and we are trying to understand with diverse ligand as well, whether they have real impact on that kind of aspects or maybe there are something more that we need to know. But some new understandings are already there, which I'll explore maybe later on, sometime whenever we'll talk about once we come up. But there are something even further mysteries there, not only just dimer. We have come across some small experiments we did, but we are waiting for further validation, and that will come up as a like. So we are trying to reach towards understanding. That is one of the aspects. Yeah.
Hi. So very nice talk. So I have a small doubt. Like you said, I understand if you are adding carboxylic acid, it is giving more photoluminescence. That's totally fine. But I feel in water, carboxylic acid will less likely to be present as a dimer compared to a organic solvent, because carboxylic acid, it will be hydrated more. So do you have any experimental proof that it is
Yeah, that was the mass spec data. That's the dimer what I talked about. I just talked about like without no experiment. We talked about, yes, we saw that in mass spec, yes.
Do you have that bond, some strength, I mean bond length, something?
We did not do any structural understanding of that. We did
Yeah.
some experiment and we did try to calculate it from the theoretician.
Yes.
But yes, we don't have a crystal structure to know like what exactly happening in that.
Yeah.
But from the mass spec data, we thought that this could be one of the possibilities.
Yes, but if you think generally, carboxylic acid will less likely to be present as a dimer compared to a organic solvent, right? Because it will be more hydrated.
Not in terms of, let's go to other aspects of that. Let's say you are thinking about hydrogen bond. I said maybe there is no hydrogen bond. It's just anchoring one carboxyl is anchoring to the other clusters. That is also possible, right? So in that, yeah.
That is also possible in the organic solvent, right?
No, in aqueous solvent also it is possible because you have CO minus. That's the basic media.
Yeah. Okay, just for curiosity, do you have any spectra to confirm that the metal and the ligand bond is present? This for my curiosity.
Yeah, we don't have it yet, but exams can be carried out and other experiments can be carried out in situ to know how exactly things are there.
Which kind of experiment we can go for?
Sorry?
Which kind of experiment can give this information?
Yeah, like you wanted to know the metal ligand interactions, right? So
if there is a bond between the metal and the ligand, how can
IR itself you can know, but that's again in solid state. In liquid state, if you have a water, then it's very hard to go to that domain, right? Around 3000 in that centimeter inverse. That domain is very difficult to know. But yes, I would say liquid state exams would be better way. We had that things in our plan, but it did not work out, depends on several other factors, because that's not so easy. That's very tricky experiment. Professor Kulkarni knows that, that how hard it is to get an exams of a good quality sample. So yeah, but that would be fantastic to get to know about that.
Okay, thank you.
If there are no students asking questions, no? How often you come across these clusters crystallizing?
Yeah, I would say it's very lucky. Sometimes, as Professor Mandal suggested, that you need to have a specific ligand sometimes. That matters a lot in order to get a crystal. And crystallization is very tricky process. Even if you try hard, it may not work. Sometimes it also works just like inorganic chemistry. But it also matters is that the cluster dissolutes after some time. So slowly the ions started leaching out, and that's basically, which is not the problem for other organic molecules. In this case, that's probably the biggest problem, that it started leaching out. And then once you have that, your impurity, whatever you thought that it's a pure cluster system in your entity, it's not anymore, right? So, and then it stops crystallizing process. But yes, now enormous number of crystallization reports are coming slowly. So it's coming out, but it's hard.
We'll talk later.
Yeah.
Indranath, very nice. You are an energetic person. I just wanted to know, you make so many clusters, you know, yesterday and today I heard many things, right? Suppose if you take rare earth elements, they have very high coordination number. And I have not seen anybody putting rare earth elements in the clusters.
That's true. Yeah, there are something like some reports are coming up on this aspect, but one of the major reasons which I do not wanted to work on this aspect. One of the major reason is that we are trying to go towards 3D aspect rather than going this aspect, because those are more costly, right? If you think of practical applications, then again it goes back to the same situation. But yes, that would be a fantastic experiment to do, and putting up rare earth where you have more and more coordination. But if you put rare earth, there will be one thing. If you have a carboxylate and other amine group free there, right? So they will immediately form bond there itself. So rather than forming an alloy or forming in clusters, they will remain as that oxidation state +2 or +4. There is a high possibility.
Oh, I see. But I think, the chemistry is very rich there.
Yeah,
also.
yeah, yeah.
That's what I am
absolutely.
saying.
Absolutely, yes.
So there should be some kind of a marriage between nanoscience and then rare earths.
Definitely, yes,
So
yes, yes,
that-
yes. The field is exploding.
Yeah,
hasn't
yeah. It's a lot of future.
Exactly, yeah.
Yeah, I have a comment related to the question about how difficult it is to crystallize these molecules. And I don't want to sound too egocentric, but whenever you put carboranes on the surface, they will start crystallizing.
So that's the next thing which you need to work on, yes.
So next year, when we have a cluster session, I assume we might see lots of carborane clusters being on the metal clusters, and we'll see lots of new crystal structures.
Okay, thank you.